Hello students and welcome to HSC Chemistry, the acidic environment topic. This is the first. It's not chronologically the first because there's already been a few videos made before this one, but in terms of conceptual understandings, this is the beginning of the acidic environment topic. So in this video, we're going to have a bit of a look at indicators. Indicators are dyes which change color in different solutions, acidic or basic solutions. So that is solutions with different pH values. Because an indicator is a pigment, we need to make sure that there will be a range of different colors for the indicator so that we can get some sense of whether the solution is in the acid or base range. Now, most indicators are actually buffer solutions, and that's a term that we'll look at later on. They're a combination of a weak acid and its conjugate base. And for those of you who've been watching this in the context of what we've been doing in class, you will understand this term conjugate. For those who haven't covered that yet, that's something that will come later on in the course. But effectively, what we need is two species with two different colors, so A and B, and we have an equilibrium existing between them, and each of them has a different color, color 1 and color 2. And when the equilibrium is on the right, then color 2 will dominate, and then when the equilibrium is to the left, then color 1 will dominate, and there will be occasions where you'll have some point in the middle where the two colors may coexist with each other. Some of the common indicators that we have used, that you may have used before too, or that will be very important, particularly for those of you carrying out some titrations. Methyl orange. Methyl orange is red in the strong acid range and yellow beyond about 4.4. And then it's orange in this little transition where the red and the yellow both coexist. And the transition here is between about 3.1 and 4.4. Another important one is litmus. You'd be familiar with litmus probably from your junior classes, which is red in acid and blue in base. And then purple in this mid-region here, which is around about neutrality, around about 7. And again, for those who were looking at titrations, we have phenolphthalein. Phenolphthalein is a great indicator because it's colorless, no color at all in acid solutions and in neutral solutions, and only between about 8 and 10 where it shifts to this beautiful bright pink color. So let's have a look at each of these indicators, or at least a couple of these indicators, in a little bit more detail. So firstly, litmus. Unionized litmus is dominant when the pH is less than 5.5 and our solution is red. Now, of course, we also know that litmus can exist as a paper where the paper's been dipped in litmus and has taken on that color. And then when you put that piece of paper into different solutions, they'll either remain red or they will turn blue. So the red color is when the acid is dominant, and the blue color is when the base is dominant. And then if it's a liquid, then we can have both the red and the blue existing together in that mid-range, and that means that we should have a solution that has a purple color. The transition is what is important, and it's particularly important for those of you who've already started looking at titrations and are having to select indicators that are appropriate to the particular reaction that you're carrying out. A couple of important things about this scale. You can see that it's red in the acid range and it's blue in the base range. Again, it is litmus. But we can also see that we can express these as pH. So these are neutral solutions around here, neutral solutions in the middle, and pHs that are very low have an acid, are acid solutions, and pHs that are very high are basic solutions. Basic. Blue is basic. And then we have this region in the middle where the transition occurs. And the transition is going to be very important, but more for when we're looking at, as I say, acid-base neutralization reactions and trying to find endpoints and equivalence points. One of the ones that wasn't on the other chart was universal. Universal is probably a fairly common indicator with which you may be familiar. And of course, the thing with universal is it has a huge range of different colors that correspond to different values of pH. So strongly basic solutions around here, pH 14, and they're purple. Then in the region around neutrality, they're green. And then in the acid region, orange to red. So quite a different range of colors because the universal is a combination of different indicators, so they're all being expressed at different times, which is why we get a range of different colors. And like litmus, universals can be used as a solution with dropper bottles, or it can be soaked onto a paper as this one has been. Phenolphthalein is a great indicator, and a little meme here for one of my students who likes chemistry jokes. And this particular one is fantastic. And for those of you who've been carrying out your titrations, whenever we're using a strong base, this is our indicator of choice. And that's because in acidic solutions or in neutral solutions, it's colorless, no color at all. And then once it shifts into the base range above between about 8.5 and 10, the pink color starts to kick in. It's a nice bright pink by the time the pH gets to around about 10. So it's great for looking at the end point of titrations because the color just jumps out at you, and you're not trying to look at a different shade of red or orange or blue or green. It's very clearly a color or it's colorless. So phenolphthalein is one of the great indicators and one of the ones that we do use, particularly with strong bases. If we have a weak base, phenolphthalein is not so good, and so when we're titrating against a weak base, then we will use methyl orange. And that's because it's red down in the low pH range, so pH, say, around about 1 to 2. It's orange in the transition, so between 3.1 and 4.4, methyl orange is orange, and beyond that, it is yellow. So pretty much, yellow. Pretty much anything above 4.4 is going to be a yellow solution. So this is one of the reasons why we use it when we're titrating a weak base against a strong acid. We won't titrate a weak base against a weak acid because that would be pointless and it would just take too long. Both equilibrium systems and very little change in their overall pH. So we don't do that. So methyl orange is our one of our choices where the base is weak and the acid is strong. So here's a question for you. Question 7 out of the 2014 paper, and hopefully even by this stage you might realize that the first 20 questions, 15 to 20 questions of the HSC papers have been multiple choice. So I've just changed this a little bit to make it a little bit more challenging, and so we can show a process. So what I want you to do is have a look at each of these statements, 2, 3, and see if you can use the table to classify the substance, giving you a reason. You might want to stop the video at this point, or at least pause it. So if we're going to try and solve this problem, what we have to do is to see what each of these statements actually means. Methyl orange turns yellow when the pH is greater than 4.4. So therefore, all methyl orange turning yellow tells us is the pH must be greater than 4.4. Likewise, with methyl red, we know that it's yellow up here in the top range as well, and so therefore that means anything above 6.2. So now we know that the solution must be greater than 6.2. So it can't be 5, for example, because that would fulfill the first condition, but not the second. When we look at the third statement, phenolphthalein remains colorless. So if it remains colorless, colorless is here. So that means it's in the bottom part of the range, therefore it's less than 8.3. So it is less than 8.3. This means that our pH range must be between 6.2 and 8.3. So this is a reasonably neutral solution. And that's because all we can do is tell that the range must be greater than 6.2 because it's yellow in methyl red, and less than 8.3 because it's colorless in phenolphthalein. Thanks for listening.